Hey there, this is some more covalent bonding. We're going to do day 2 and draw some more structures and find out how they're all put together. Okay, so valence shell electron pair repulsion is a mouthful, so we just call it VSEPR. It's the model that we use to determine the molecular shape. It's not just a flat, one-dimensional structure. It's actually a three-dimensional structure, and we're going to kind of show you how, based on this VSEPR, how the molecules are put together, and the bonded, how the bonded and unbonded electrons have a great deal of influence on the shape of the particular molecule that we're talking about. So VSEPR, another thing that it does is it will show us the best arrangement that will minimize repulsion between atoms. Okay, because they're wanting to push away from each other because they've got those same charges. So we try to minimize that as much as possible. So I'm going to draw first the structure for carbon dioxide. So just a reminder, carbon dioxide, CO2. Carbon has 4 valence electrons. Each oxygen has 6 valence electrons times 2, so that'd be 12, for a total of 16 electrons in our structure. All right, so we'll draw carbon in the middle, because remember, if there's carbon, it gets center stage. So we'll draw 2 bonds here, hook up each of the oxygens, and we'll start checking for an octet. Well, first off, I notice that carbon does not have an octet, and it likes to have 4 bonds, so we're going to double bond that. Can we double bond that? Yes, we can, because they're both part of CNOPs. That's the only way we could double bond it. So yeah, we're going to double bond that thing. Then carbon would have 2, 4, 6, 8 electrons around it. Oxygen is still sitting here with 4, so we'll put a couple of lone pair on oxygen like that. Okay, and check for the octet. So 2, 4, 6, 8, 2, 4, 6, 8, and carbon has 8. So that looks like the best structure for our carbon dioxide. So once we draw that structure, we can see the way everything's put together. This is called a linear molecule. Okay, carbon dioxide is an example of a linear molecule. The way that you will know a structure is a linear molecule is it will have 2 bonded atoms. See, there's a bonded atom, there's a bonded atom. See, 2 bonded atoms. It doesn't have any lone electrons on the center. There's no lone electrons there. Okay, it has some lone pair out here, but none on the center. Its angle, its geometry, 180 degrees. You know that. I hate geometry, but it's 180 degrees. You know that. It can be symmetrical or asymmetrical in shape, meaning that this could be an oxygen, this could be a fluorine. Okay, it doesn't have to have oxygens on each side, but in this case it is very symmetrical. It looks exactly the same from this way and this way. Okay, it looks exactly the same. Carbon dioxide is an example, and beryllium dichloride is an example. This is a simulation of what carbon dioxide looks like. So we'll go to this PhET simulation and look at carbon dioxide. And let that load. Okay, we're going to do real molecules because we want to see carbon dioxide. Okay, see how carbon dioxide is? Now look down here. When you see the structure that I drew, there's lots of electrons on the outside of those oxygens. They're not going to want to be close to one another. Why? Because they're both negatively charged. So look, every time I try to push those oxygens closer to one another, they repel one another, and they stay as far apart as possible. It's a nice linear shape. Okay, we'll show you the bond angle, 180 degrees. Oh, still going to pop back to 180. Okay, so that is the molecular geometry. See, it's linear down there. All right, so let's go back to our notes. There we go. So we'll do more of these. Now we're going to draw the Lewis structure for water. Let me get rid of that. Okay. Water, H2O. Okay. Hydrogen has 1 valence electron, but there's 2 of them. It's 2 plus. There are 6 valence electrons in oxygen. So 2 plus 6 would give me 8 total electrons in my structure. So what would go in the middle here? Well, I know that hydrogens are always terminal. So I put oxygen in the middle, and I'm going to bond each of the hydrogens like that. Okay? Each hydrogen has an octet because remember, hydrogen's an exception to the octet rule and it only gets 2 electrons to be happy. Well, oxygen doesn't. Oxygen gets 8 every time. So I need to put those in as lone pair. So I could put them all on one side. I could put them opposite. It doesn't really matter. But the truth is, when we put the lone pair electrons on a structure like this, they actually do go on the same side of the molecule. When they do, these lone electrons take up a whole bunch of space, like that. Okay? So that causes these bond angles to move. Okay? It pushes them down. The lone pair electrons take up a lot of space. Alright, so we're going to draw those bonds like that and hook our hydrogens like this. Okay, so this is more like the shape of water. Okay, got a lot of electronegative area on this side because of all the electrons, and then more electropositive on this side. Okay, this is a little more negative up here, a little more positive down there. Okay, water is a polar molecule. So anyway, so this is the structure for water, and so we'll go on to, oops, not clicking, there we go. This is called a bent molecule. Okay, you didn't really need the Mickey Mouse ears right here. I was just showing you they take up a lot of space. They're like the playground bullies. Okay, these lone electrons, they travel in pairs and they push the bond angles away. All right, they push the bonds away. How do I know that this molecule is a bent? Yep, bent. You would think it would be some fancy name, but it's not. It's just called a bent molecule. So a bent molecule is characterized by 2 bonded atoms. 1, 2. So it's got 2 bonded atoms. It's also got 2 lone pair of electrons right there. Every bent molecule will look the same. There will be 2 bonded atoms, each hooked with a bond, and there will be 2 sets of lone pair electrons. The bond angle is 104.5 degrees and it is asymmetrical. So what I mean by asymmetrical is that way. Okay, yes, it looks the same from this side to this side, but it definitely doesn't look the same from that side to that side. Okay, it's got this electronegative element or area right there. So let's look at the PhET, see the simulation of water. Okay, shut that, there we go. All right, so we're going to do real molecules because we want to do, there's water. Okay, look what we got there, look. Look how much space those lone pair electrons take up. Okay. And they are constantly pushing those bond angles down. I can try to get the bonded electrons, the bonded hydrogens close to it, but they just won't do that. All right. So we'll look, there they are, the lone pair electrons are in there. See, up here and back here. Here, trying to straighten it up a little bit so you can see everything, kind of. There we go. That's a little better. Okay, so it is a bent molecule. Okay. I'm not going to handle that right there. It's a bent molecule, and look, there's our bond angles, 104.5. You can kind of see right there. Let's see if we can. It doesn't matter if we move them closer; they'll end up. There you go. See, at 104.5 for those bond angles. Okay, the lone pair electrons, playground bullies, pushing those bonded angles or bonded electrons, bonded atoms, bonded hydrogens down like that. So it'll look like this bent molecule down there. So let's go back to, oh, sorry about that. Oh no, wrong one. There. Ha! I'm back. Okay. So now we're going to draw the Lewis structure for boron trifluoride. Okay, BF3. So BF3. Okay, how many valence electrons does boron have? It's got 3. How about fluorine? Fluorine has 7 valence electrons, and there's 3 of them, so 7 times 3 is 21. So I will have 24 electrons in my structure here. Okay, so what goes in the middle? We're going to put boron in the middle here, boron, least electronegative, and then we're going to hook as symmetrically as possible. You know, I'm not the greatest drawer ever. As I can, there we go, the fluorines. So we'll bond the fluorines, each bonded 1 bond. Okay, then we're going to look and see who has an octet and who doesn't. Does boron have an octet? Ooh, you can't see that whole thing. Let me see. Let me put it up there a little bit more for you. There we go. Here. Does boron have an octet? Yes, it does. Because remember, there are 3 atoms. Hydrogen gets 2 electrons for its octet. Boron gets 6. Beryllium gets 4. So boron has its octet. I wrote it right up there. Sorry about that. I wrote it right up there. So boron does have its octet. It has 2, 4, 6 electrons, so it's got its octet. So I'm going to put the remaining electrons around the fluorines to give them an octet. Put them in as lone pair electrons. Here, I think it'll be easier. You see more of it. There we go. Look at that. There you go. You can see lots more of it now. So I put in those lone pair electrons. Remember, we got to count and make sure that we have all 24 in there. Okay, so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Check. We've got them all. Okay, this is called, get there, a trigonal planar molecule. Okay, this is characterized, you'll always know a trigonal planar because it will have 3 bonded atoms. 1, 2, 3 bonded atoms. No lone electrons. That should say no lone electrons on the center. Okay, boron does not have any central electrons here. None on that central atom. So 3 bonded atoms right there. No lone electrons. Bond angles are 120 degrees. Could be symmetrical, could be asymmetrical. Okay, looks like boron trifluoride, pretty darn symmetrical. So, oops, sorry. All right, so now we're going to go and look at the FET for boron trifluoride. Get there. All right, we're going to do real molecules and see if we can find boron. Oh, there it is, boron trifluoride. Okay, so you see, that's what boron trifluoride looks like. Okay, they're all very nicely spaced. They repel one another, so they're trying to stay as far apart as they possibly can, but they don't change any. So it's a trigonal planar, okay, because it's in a single plane. Tri means 3, trigonal planar, so it's a trigonal planar molecule. Bond angle is going to be 120 degrees, here to here, here to here, here to here, all 120 degrees, all those bond angles. All right, let's go back to the notes. There we go. Okay, so that was boron trifluoride. So now we're going to draw the Lewis structure for ammonia. Okay, I'm going to make this even a little bit higher so I can get even more of it in there. Okay, I want to get it all in there without. There. So the Lewis structure for ammonia, NH3, nitrogen trihydride, all those names are applicable. Nitrogen has 5 valence electrons. Each hydrogen comes with 1. So 1 times 3, 3 electrons. Total of 8 electrons in this structure. I'm going to put nitrogen in the middle, and I'm going to bond as symmetrically as possible the 3 hydrogens. Now I'm going to check for octets. Well, each hydrogen has an octet because it brings 1 and it's sharing 1. So each hydrogen has its 2 electrons that it wants. Well, nitrogen is not an exception to the octet rule, so it wants 8 electrons. So I need to put a lone pair of electrons here on nitrogen, so I'm going to move the hydrogen so that I can have that lone pair. Because remember, when you've got those lone pairs, it's like the playground bully, they're going to push the other bond angles down and away. Okay, this molecule, as it's drawn, kind of sideways, is called a trigonal pyramidal molecule. Okay, so look, tri means 3. Pyramid is like a 3-sided pyramid. Look, see how it looks up here? That's much better drawing than mine. Okay, it's a trigonal pyramidal. This is characterized by 3 bonded atoms. Okay, there's 1, 2, 3 bonded atoms, and 1 lone pair on the center atom. There's my lone pair on the center atom. Okay, it will make a pyramid shape. This lone pair of electrons going to take up a lot of space there and push all these bond angles away. Okay, so it'll look like a pyramid. The bond angles are 107.3. That lone pair takes up more space than an atom. It's, like I said, it's like a playground bully. It takes up lots of space. Its shape is asymmetrical. Oh, look, see, looks different that way and different that way. It is not symmetrical, definitely. So let's see the PhET simulation for ammonia. Real molecules, and see, let's find ammonia. There it is, NH3. So there's our playground bully, the lone pair electrons. It's trigonal pyramidal. Okay, it pushes the bond angles so that it looks like a little pyramid. Okay, it's a little three-sided pyramid. The lone pair electrons take up a lot of space, pushes those bond angles down. Kind of looks like a pyramid. Okay, bond angles 107.8 degrees. Okay, let's go back. Okay, next molecule. Let's draw the Lewis structure for methane, CH4. There's CH4. Carbon comes with 4 valence electrons. Each hydrogen comes with 1. 1 times 4, 4. So I will have 8 electrons in my structure. I put carbon in the middle because carbon always goes in the middle. If there's a carbon, I'm going to bond each hydrogen with 1 single bond to the carbon. Carbon will have its octet, 2, 4, 6, 8. Each hydrogen has its octet, 2, 2, 2, and 2. So this structure, it's a valid structure. It's all done. Everybody's got their octet. This structure is called a tetrahedral structure. Okay? You'll know that a molecule is tetrahedral if it has 4 bonded atoms. See, look, 1, 2, 3, 4 bonded atoms, and no lone electrons on that center. No lone pair on that central atom at all. The bond angle is 109.5. It could be symmetrical, could be asymmetrical. There could be different things bonded to this center atom. I know. There we go. Now we're going to look at the PhET for methane. Get there. Real molecules, and we will pick CH4 carbon tetrahydride. So there it is. All right, there's our little tetrahedral molecule. So you can try to push them together, but they don't want to stay together. Okay, those bond angles will stay at, oh, I was going to show you the bond angle. There we go. At 109.5. Okay, you can try to change them, but yeah, they're going to push back apart from one another. And that is a tetrahedral molecule. All right, tetrahedral. And let's go back to our notes if your teacher can do it. There we go. All right, so we're going to draw the Lewis structures. Okay, we're going to use our new rules and see if we can't remember the new rules. So the first one I'm going to do is iodine. Okay, iodine. Valence electrons. Iodine has 7 valence electrons times 2, so I need 14 electrons in my structure for iodine. There's 2 iodines. What's the central atom? Well, it's not a central atom. It's just 2 iodines. So they're hooked together like that. 1 single bond. This is not going to be a double or triple bond. Why? Because it is not part of the club CNOPS. Nope, sure isn't. So I need to put lone pair electrons, around each iodine to give them their octet. And then count to make sure that I have 14. 2, 4, 6, 8, 10, 12, 14. Check. 14 electrons. What shape is that? Just 2 bonded atoms right next to each other. That's a linear. That's a linear molecule. Sure is. Nothing on the center there. No center. Okay, let's try the next one. Hydrochloric acid, HCl. Hydrogen has 1 valence electron. Chlorine has 7, for a total of 8 electrons in my structure. Which one's going to be the central atom? Okay, well that's kind of a trick question. They're just going to be next to each other. There's not a center here. So put chlorine on one side, hydrogen on the other. Hydrogen has its octet already. When it has one and it shares one, it brings one to the party and it shares one of chlorine's. So I'm going to put the remaining electrons around chlorine as lone pair. Chlorine has its octet also, 2, 4, 6, 8. So total of 8 electrons in my structure. What type of molecule is that? What shape? It's a linear molecule. Okay, just a straight linear molecule. All right, ammonia. We did ammonia. But I'm going to show you again. I'm going to do it again. Nitrogen has 5 valence electrons. 3 hydrogens is 3. 8 total electrons. Draw nitrogen here. Hook my 3 hydrogens. There, there, there. Each hydrogen has an octet. Nitrogen doesn't, so I put a lone pair of electrons there. That lone pair takes up a lot of space, so make sure these bond angles are pointed away, like that. Do you remember what kind of molecule has 3 bonded atoms and 1 lone pair on the center? It's trigonal, pyramidal. There. Okay? Always characterized the same way. They're always going to have 1 lone pair on the center atom, 3 bonded atoms. Okay. Oxygen difluoride. Oxygen has 6 valence electrons. Fluorine has 7. 7 times 2 is 14. So I have 20 electrons that I'm going to put in this structure. I'm going to put oxygen in the middle. Fluorine, or the halogens, they like to be terminal, so they like to be on the outside. So I'm just going to start by drawing it right here. I can always change it. I need to go ahead and give fluorine its octet. Okay, 2, 4, 6, 8, 2, 4, 6, 8. Oxygen does not have an octet though. Look, it only has 2, 4. So we are going to put them, remember the lone pair is going to want to hang together. We're going to put them on this side. Okay, they're not going to go on opposite sides. They're going to go on this side. When they do, what happens? It pushes the bond angles away. Okay, we'll fill in our lone pair again. Okay, what molecule had 2 lone pair and 2 bonded atoms? It has the same, has exactly the same characteristics all the time. 2 lone pair on the center atom, 2 bonded atoms. It's bent. It's a bent molecule. Okay. We do a couple more. Yep, there we go. Okay, carbon has 4 valence electrons. Hydrogen has 1. Chlorine has 7. 7 times 3, 21. So let's add up all these electrons. It's 5, 5 and 21, 26. Always check my math. Okay? Of course, you can't let me know that I'm wrong today, but, you know, if you see me doing the math wrong, it happens. So I need to put what in the middle? Exactly. Carbon goes in the middle. Hydrogens and those halogens tend to be terminal. Hydrogen's always terminal. So we'll put carbon in the middle. We're going to hook chlorine, 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 and a hydrogen, each with a bond. Well, carbon has its octet, 2, 4, 6, 8. Hydrogen has its octet. We're going to put lone electrons here on chlorine, right there, and check to make sure that we have 26 electrons and we didn't just throw tons of electrons in here where they shouldn't be. Okay, there's only so many at the party to go around. So we check to see if we have 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Check. What shape is that molecule? Has no lone pair on the center atom and 4 bonded atoms. It's tetrahedral. You may need to go back and look at your notes. Okay? Make sure that you're doing these right. The characteristics will always be the same. You can predict what shape it is based on the number of bonds and the number of lone pair and where everything is. Okay, so we'll do F. Carbon has 4 valence electrons, but there's 2 of them, so it's 8. Plus 2 from the hydrogen, 10 in this structure. So what goes in the middle? There's 2 carbons. Which one goes in the middle? Yes, they both go in the middle. Because remember, carbon has that special property that it can be bonded to itself. All right, so we put those 2 carbons here. Hydrogens are terminal, means they're on the ends, so I'm going to put the hydrogens there. Then I'm going to check and go, oh, the hydrogens have their octet, but neither one of these carbons do. This carbon has 4, this carbon has 4. So, yes, we could put lone pair on there, but are you sure that's the best idea? Carbon doesn't like lone pair. Carbon likes bonds. Is carbon part of CNOPS? It sure is. So that means it could double or triple bond. So let's see if by triple bonding these two carbons gives us our octet. So that's 2, 4, 6, 8, 2, 4, 6, 8. So check the octet. That's good. So let's check to make sure we've got 10 electrons. 2, 4, 6, 8, 10. Perfect. Okay, what shape is that? It's just in one long line. Linear. It's a linear molecule. Okay, starting to see how these work? Okay, let's do one more. We've already done carbon dioxide once, but let's do it again because it's in here. CO2. So carbon has 4 valence electrons. Each oxygen comes with 6. 6 times 2 is 12. So I have a total of 16 electrons. Carbon goes in the middle because carbon's always going in the middle. I'm going to bond each oxygen. Okay, carbon does not have an octet. Carbon and oxygen are both part of CNOPS. So I'm going to double bond the carbon to each oxygen. And then I'm going to go ahead and put some lone pair electrons out here on oxygen. Then I'm going to check to see if I have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Check. What's the shape? It's linear. There's 2 bonded atoms, and there's no lone pair on the center atom. It's a linear molecule. Okay? So, there's the bell. Do your homework. Do some practice. Take a quiz. And ask questions if you have questions.